hi guys. We are going to have the second tutorial today. And basically I'm going to look at a few examples of the kind of things that we have talked about over the past few weeks. Maybe in some cases trying to mix and match. And obviously the recent topic of interest has been this. So anyway, let's do a couple of examples, or a few examples. So let's start with this one. Find the equivalent resistance. And this is the circuit. We are looking between 2 points like this. That's it. So maybe spend a few minutes on it, see if you can do it on your own. So this is where we are looking. Equivalent resistance between those 2 points, between the two wires that are sticking out. Okay, so let's take a look together. Now this is, you might say this is a decent sized circuit. And at first sight, it's hard to spot things maybe a little bit. Do we have anything that's in series or in parallel with anything else? I don't see any, but I'm hoping you guys would correct me if I'm wrong. So there are maybe some of the patterns that we recognize. For instance, in the middle here, we have this, which is a delta. And so you could replace this with a Y shape, right? And that would be like this. So if I replace that delta with a Y, things start to look a little different. And then maybe I can start doing some combinations. For instance, the 6 ohm here then would be in series with the bottom left leg of that Y, correct? And so maybe that way I can make the circuit a little simpler. And similarly, maybe I could then combine this with the 4 ohm resistor down at the bottom right, and so on. So then work my way through. But again, like I've said in the past, you always want to make sure that you take a good look at the circuit, try to develop some insight into it before you launch into a sort of brute force solution, right? So in this particular case, are there other patterns that I can recognize? Is there something else that I can? Maybe a bigger chunk that I can recognize? What do you guys think about this? Does this look like something? Like a Wheatstone Bridge, right? So if I redraw this, I have this, 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 this. I've just brought basically shortened this long wire at the bottom, right? So I have that connection. And then I have the other stuff around it. Let's make sure I'm doing this correctly. So I've got the 5 ohm, 10 ohm, 4 ohm, 8 ohm. Correct? And so this is the 3 ohm, 2 ohm, 5 ohm, 6 ohm, 4 ohm. So is there something, so I've just redrawn the circuit. Is there some simplification that I can get from this? So is the Wheatstone bridge condition met for the circuit in the middle? So recall the Wheatstone bridge condition. If you look at the diagonally opposite resistors, so I have 3 ohm and 4 ohm resistors on the two opposite sides, and then 2 ohm and 6 ohm resistors on the other opposite sides. So because 3 times 4 is equal to 6 times 2, that condition is met, which means what is the voltage difference across the 5 ohm resistor? 0. There's no current through the 5 ohm resistor. So there is no current through the 5 ohm resistor. So if there is no current through that resistor, if there is no current through the 5 ohm resistor, what can I say about the condition in which the 3 ohm and 6 ohm resistor find themselves? They are in series, right? Although on paper they don't look on series, but if things are such that there is no current through the 5 ohm resistor, then those two are effectively in series. And this is regardless of what you are connecting between the two inputs of the circuit. So we are interested in the equivalent resistance of this entire circuit, and regardless of what you have connected at the top. So let's say you have applied the voltage to measure the current that goes through so that you divide the two and get the resistance. Regardless of that, because you have the Wheatstone condition, there is nothing going through the 5 ohm resistor. And so you can essentially say that that is not there. And so you have 2 resistors in series, another 2 in series, and then the combination in parallel. So you have 9 in parallel with 6 ohm, right? So that simplifies greatly. And now let's look at the rest of the circuit. Let me put that back in there. So this chunk then gets simplified greatly. So then the part in circled in red is simply that. Three, 6, 2, and 4. Which gets simplified. So once you do this now, imagine you have replaced the entire part that's circled in red with one resistor, the equivalent of those. Then what do you have for the whole big circuit? That's another Wheatstone bridge, right? And you see that the Wheatstone condition is met again. 5 times 8 equals 10 times 4. The big circuit, or the full circuit, is another Wheatstone bridge. Because 5 times 8 is 10 times 4. And by the way, you see immediately that actually the outer Wheatstone bridge, the bigger chunk of the circuit, forms the bridge regardless of what's in the middle there, right? So even if what I had in the middle there did not satisfy the bridge condition, you didn't actually need to solve for what's in the middle to get the answer here, right? So the answer here is simply 5 in series with 10, and that combination in parallel with 4 in series with 8. Okay? And in fact, this was regardless of the condition of the internal portion. So our equivalent is, like we said, 5 plus 10 in parallel with 4 plus 8. So that's the sign for in parallel. Okay? So that's just another example of the kind of thing that I'm hoping you will get used to looking for. And you know, it's not always the case that you have these things, but at least you will get a feel for what's going on in the circuit, even if you don't find a pattern like this. So be careful before you launch into a brute force approach. Try to develop an understanding of the circuit. Okay, any question on that? Okay, so now I want to do an example of a Norton equivalent. So find the Norton equivalent that the 10 ohm resistor sees using superposition. Okay, so we have this circuit. There's a 10 ohm resistor right there. And what I'm asking for is the Norton equivalent of the circuit that 10 ohm resistor sees between its two ends. Okay? I'm asking you to find this using superposition. Again, think about the approach rather than try the numbers. All right, let's take a look together. So first of all, it's very important to look at exactly what I'm asking for here. So I'm saying the property of interest is the Norton equivalent that the 10 ohm resistor sees. So this 10 ohm resistor between its two ends is seeing the rest of the circuit. Okay, so itself is not part of the circuit, the Norton equivalent that I'm interested in. So maybe to illustrate that better, what we're really looking for is what's going on between these 2 points, excluding the 10 ohm resistor itself. Okay, so I could have also equivalently asked this: what's the Norton equivalent between these 2 points without having included that 10 ohm resistor? Okay, so it's very important to pay attention to the detail of what one is after. And so for that purpose, really this is our box, excluding that 10 ohm resistor. And we are looking from the outside. Okay? So that's a key point to keep in mind. Now, if we are interested in the Norton equivalent, we are essentially trying to establish the IV characteristics, that straight line that goes through that crosses in general, not the origin, but crosses the current and voltage axes on 2 distinct points. And so one way to find the equivalent, then, as we've talked about before, is to find the open circuit voltage and short circuit current. So if this is my voltage versus current between these 2 points, this is the open circuit voltage, and this is the short circuit current. And one way to find the Norton equivalent was to find these. Now, we could equivalently find any other 2 points on the line, and you could still kind of define the line entirely. But these are convenient. So, open circuit voltage, pretty straightforward. So basically, we leave the circuit as it is and find what the voltage is between those 2 points. So if I call this VOC like that, right? That's basically what I'm looking for, right? So we want to do this with superposition. Now, to do this with superposition, what are my steps? So first of all, need VOC. So I'm just leaving the circuit as it is, but I want to solve it using superposition. What should I do? So we need VOC using superposition. So what should I do for using superposition to solve this circuit? Yeah. So using superposition means we have to find the effect of each independent source. This is very important. Each independent source alone, and then add up the results. And taking the signs into account, right? So paying attention to the signs. So again, if this is the direction I'm defining my voltage, okay. So here I have only two independent sources, the 8-volt source on the left and the 8-amp current source on the right. The other two sources, they are both controlled sources. They're not independent sources. And one of them is a current-controlled current source, the 5I1. And the other one is actually a voltage-controlled voltage source, the 2V2. Okay? Those have to remain intact in the solution in each step. Okay, so you would have one circuit to solve in which the 8-volt source would be set to 0. So basically, you would replace this with a wire like this. And so now you have a circuit that has only one independent source, the 8-amp independent source. Now you have to solve this circuit. Now it's a relatively big circuit, and you have to solve it. You can solve it using any method that you know. Now, for instance, you can also use nodal analysis. And we'll spend a little bit of time doing nodal analysis for this later on. But in general, you can solve it using your KVLs and KCLs. So that's one step. So remember that the voltage source, so step 1.1 is set the voltage source to 0. Which is a short circuit. And we should say the independent voltage source. And find V. For instance, using KVL, KCL. Step 1.2 would be to set the independent current source to 0. Which in this case means open circuit. For a current source, it means open circuit. And find V. And the third would be add up, including the sign in your calculation, the two values. Okay, and so when you try to set the current source to 0 to see the effect of the voltage source, here, what happens is this. That source is gone. That's an open circuit there. And now you just solve this new circuit to find the value of V between those 2 points that are indicated at the top. Okay? So that's the first step, to find the open circuit voltage. Then 2, need the short circuit current. Okay? But the approach to superposition is the same, except that you have to pay attention that now you have to actually change the circuit. So now you have to do something like this. So now the voltage there is going to be 0, you're interested in the current going through this wire. Which way should I indicate the direction of this current to be? So remember, this is how I had defined my voltage. Right? So now I have set the voltage to 0, and I want the current, because I'm after a Norton equivalent. So I want the short circuit current. Which way should the direction of the current be? Well, let's remember the Norton equivalent. The Norton equivalent circuit. So I have something in the box like this. So this is IN, and this is RN. Okay? So the IV characteristics that we've defined, as shown on the graph on the top right, this is how we define the voltage. Which way did we define the current? Like this? Good. Yeah, very good. So you see, this is a matter of being consistent with the way we have defined our things up there, because you can see here that if that current I increases in the circuit, so if you connect something here that takes some of the current outside the box, then you have less current going through the RN resistor, and so the voltage between those 2 points actually drops, right? So the way I have defined my IV characteristics is consistent with such a direction, the definition of directions being like this for V and I. So I have to keep in mind then that if I had defined my V like this, with that polarity, my I has to be like this. Okay? You see, so although, as always, you can choose a convention that you want, but you have to stay consistent for each problem within your choices, right? So we'll say here, pay special attention to the direction. And so then the rest is the same. You look at the effect of the 8-volt source once, which means you open the 8-amp source, replace it with an open circuit, and you calculate the current I going through that green line at the top, which means you have to solve the whole circuit to see the effect of the 8-volt source. And the 2 dependent sources remain in the circuit. And then another step would be you replace the 8-volt source with a short circuit and see the effect of the 8-amp source, and then add them up. And then you have your open circuit voltage and short circuit current. And so remember that in this particular case, what's the relationship between the short circuit current and the Norton current? They're the same. Because if you look at the little box that I have up here, the green box, if I short circuit the 2 terminals, it means that the voltage across the resistor Rn drops to 0, so there's no current through that resistor, and the entire current In goes through the wire. So In is simply the short circuit current. And the open circuit voltage, well, if I don't connect anything there, In is going through Rn, and so In times Rn is that. So once you find your open circuit voltage and short circuit current, then you can immediately find Rn and In. Notice that it was also crucial that I show the direction of my Thevenin circuit here. So you would want to maybe label things like this, A and B, and say this is my terminal A, this is my terminal B. This is the way I have defined things. Okay, so that if you produce a Norton equivalent, we know which way it corresponds to the circuit. The question of direction. The next thing I want to discuss and maybe do a little more explicitly is what if we wanted to do any of these aspects. So let's say take the open circuit voltage. What if we wanted to do it using nodal analysis? Okay. Or let's take the short circuit current. Maybe it's more fun. So now take the same problem as above. But solve for the short circuit current using nodal analysis. Now you could, first of all, question, can I use superposition and nodal analysis together? Yes, you can, absolutely. There is nothing to contradict that, right? Nodal analysis does not change anything to the physics of the problem. It's just one method of solving things. So if superposition holds, because this is a linear circuit, then for each aspect, to see the effect of each independent source, there's no reason you couldn't use nodal analysis. Okay? But maybe to make it more fun, we will do it for both sources together, okay, without using superposition in this case. Okay, so what I'd like to ask you guys to do is to write down your nodal analysis equations for this circuit. So actually do it. You know, we don't need the solution to that, but do it all the way to the point of writing all the equations and putting them into matrix form. All right, I think maybe we can now take a look at this together. So nodal analysis. And this is a problem that, well, first of all, it's a relatively large circuit, and it also has dependent sources, independent sources, both voltage and current. And so it's relatively diverse. And so that's why I thought it would be a good example of this. So first of all, let's recall what we are trying to do. In nodal analysis, we are trying to find node voltages first. So solve the circuit to find node voltages. And then from that, find whatever else we need. So what we are after in this case is the short circuit current through that wire up there. That's not a node voltage. That's a current somewhere that we need. But if you solve the circuit and have all the node voltages, then eventually you will be able to calculate all the element voltage drops across the elements and currents, and then ultimately, let's say, use KCL at one of at that node right here to calculate the current that goes there. Okay, but so for now we want to focus on writing the nodal analysis equations for this. Okay, so I'll start by defining node voltages. And the first step in that is to define a reference point somewhere in the circuit. And here's sort of just my choice. You could choose anywhere. But this is one big node here. I'll call this my reference. And I'll say this is 0 volts. And then let's go ahead and label all the other nodes with voltages. So I have one node here. Let's say this has voltage V1, capital V1. I have another node here. This is all one big node. Another node here, might be a little harder to see, but that's V3. A big node here, V4. Another one here. V5. V6. And this is just one other big node, so this is V6 and this would be V7. Have I missed anything? Hopefully not. So now I have to write all the KCLs so that I can have things in terms of node voltages. And recall that we saw in the past that when doing nodal analysis, your KVLs are automatically implemented. Or most of them anyway. So now we want to go around and write the KCLs. And we need 7 KCLs because we have 8 total nodes, 1 being the reference. But once we write 7 KCLs, the 8th one will not be an independent equation. So we just need the 7. So let's start writing it at node 1. So KCLs. So at node 1. Oh, sorry. There was a resistor there. I don't know what happened. So at node 1, we have this current I1 that has already been labeled for us. Then there would be another current going here. Let's call this maybe I3. Let's reserve 2 for this one down here. I3. And then another current here, let's say I4. Okay. So my KCL1 at node 1 would be minus I1 minus I3 minus I4 equals 0. Okay. Now, I have to do the same thing for all the other nodes and then try to relate these currents through element relationships to node voltages. And because we have already done a couple of examples of these, I want to go a little faster. And so I want to do it directly here. If I look at current I1, in order to relate it to a voltage, well, I have to define a voltage. So this would be, let's say, voltage V1 that I define. And I1 is going to be V1 over R1, which is, in this case, 4 ohms. Right? But ultimately, I want to write V1 in terms of node voltages. Now, what is V1 in terms of the big V's, the node voltages? Big V1 minus big V5. Notice the polarity of the way I have defined the little V1. Okay, so this is big V1 minus big V5. And there you have it. So that's what you need to put in the first equation. So I could maybe now, by looking at this more directly, once I start gaining enough experience, I could say, look, the way I have defined the direction of I1, even if I hadn't labeled the little V1 as an intermediate step, but I could see that the direction of I1 is such that the top left is the positive polarity of the voltage, and the bottom right is the negative polarity of the voltage, if I were to write an Ohm's law without a minus sign. So this simple V equals Ri would require that the top left be positive polarity and the bottom right be negative polarity for that 4 ohm resistor. And so I could directly, with experience, start saying, well, I'll just, instead of writing all these, I'll just say directly V1 minus V5 divided by 4. And that's really basically it. That's kind of doing a couple of steps in one go that makes things a lot faster. But again, this is something that you have to judge personally in terms of how comfortable you feel with it. So it's much better to do it explicitly a few times, write these intermediate steps until you gain enough confidence with it before jumping into doing it directly. Okay? But because we've done some examples, I'll try to do it faster and more directly here. So our first equation then ends up being, even without having to resort to the definition of that intermediate V1, just big V1 minus big V5 divided by 4. Now notice the negative sign I have next to this is just from my KCL, because I'm used to including currents that leave the node with a negative sign. Okay? You might be doing the opposite. That's also fine. But for me, this is how I'm used to doing things. Next is I3. And by the same type of argument, it's simply V1 minus V2 divided by the 2 ohms. And next is I4. Now, how do I relate I4 to the node voltages on the two sides of that branch? So I4 is going through an 8-volt voltage source. So how do I relate that I4 to the node voltages? What is the relationship between the current and the voltage of a voltage source? There is none. OK. Too bad. So there is none. And I can't do anything about it. And so I'll just keep it here. We'll deal with it later. Okay. So this is really my first KCL. So that's at node 1. Node 2. Now I'll start doing things in the same way. I have I3 going in. So I have I3 minus that short circuit current minus 5I1, right? Is that how I should write it? I3 minus I short circuit minus 5I1? So let's see. So first of all, I3. I3 is going into node 2. So that's V1 minus V2 divided by 2. Should I write it like this? Is this correct? Given what I have up here, is this a correct statement? It is a correct statement, right? It's just a physical connection you have here, and you have current going in, 2 currents leaving. But on the other hand, and so you can definitely do this. But on the other hand, if you look at the way I have defined the full node there, right, that node V2 is going all the way, right? So I'd rather not introduce another current at this point in my equations that's internal to the wire of that node, right? For the purposes of nodal analysis, that wire, that all could be lumped into one point, right? I could have redrawn the circuit so that that wire is completely collapsed, right? So rather than keeping this additional current there, I'll just really follow the way I have indicated the node which if you look here, is this whole thing, right? So what are then the things that go into the node and out of it? There is I3 going in. There is 5I1 leaving. And then on this side, there is this current and that current. Okay, if I consider the full node, that's what I see. Okay, again, nothing wrong with the statement I had written, but I want to just deal with the full node in one go. So I have I3 going in, V1 minus V2 divided by 2, then minus 5I1. Now, I1 itself, we've seen before, is V1 minus V5 divided by 4. So minus 5 okay. Then on the other side, I have, let's say, this current going into the node. Now, what is that current? That's the current through the 3 ohm resistor. So that's V3 minus the other side, which is V2 divided by 3. So that's going into the node. Okay. And then finally, I have this current leaving. That's V2 minus V4 divided by 2. If we go to node 3, then we have 5I1 going in, and I1 is V1 minus V5 divided by 4. 5 times that minus V3 minus V2 divided by 3. Node 4, I have the current from the 2 ohm resistor going in. That's V2 minus V4 divided by 2. And then I have the current in the 3 ohm resistor, if I draw it like this, plus V5 minus V4 divided by 3. And then the 8 amp going in. Node 5, I have the currents from the 4 ohm, 5 ohm, and 3 ohm resistors. But then I also have to deal with this. So let's call this some I0 here. Okay. So I have I1, which is V1 minus V5 divided by 4, plus I2, which is 0, this reference here, minus V5 divided by 5. So plus the current I2, which is 0 minus V5 divided by 5. Minus the current leaving through the 3 ohm resistor. That's V5 minus V4 divided by 3. Minus that I0 that I have indicated. And that I0 doesn't have a direct relationship to the voltage there. So I just have to keep it as it is. At node V6, I have I0 going in and this current leaving. And that current that's leaving is V6 minus V7 divided by 8. And at node 7, I have that same current, V6 minus V7 divided by 8 going in, 8 amps leaving, and then also this current going in. That's 0 minus V7 divided by 12. So V6 minus V7, V6 minus V7 divided by 8. Plus 0 minus V7 divided by 12. Minus 8 amps. So these are my 5 KCLs. My 7 KCLs. Now I have all the 7 voltages that are unknown, but I also have the little current I0 and I4, the currents of the voltage sources, be it dependent or independent voltage sources. Their currents are unknown. So I have 7 equations and 9 unknowns. But there is a couple of other pieces of information here that I have, which I haven't used yet. What are those? First of all, so those are the pieces of information that come from the voltage sources. That they introduce this new unknown for me, but they also do their share of providing information. So if you look at the 8-volt source, well, an 8-volt source between those two nodes, the reference and V1, what does that mean? If you want, this was the equivalent of KVL, that the voltage of the element is just the difference of the node voltages on the two sides. So 8 volts is the difference between V1 and 0. Right? So that's another piece of information that we already have. So additional pieces of information. V1 minus 0 is 8 volts. The other one comes from the other voltage source, in this case, a dependent voltage source. But the difference between V5 and V6 is the voltage of that dependent voltage source. Right? That's 2 times little V2. So V5 minus V6 is 2 times little V2. Two times little V2. But little V2 itself is this voltage here, which is the difference between reference 0 and V5. So that's 2 times 0 minus V5. There you go. These are the 9 equations. They don't even fit in one screen, but the 7 KCLs plus the additional 2 pieces of information. And actually, one of them is very good because it immediately gives me one of the values. Okay? So there you have your nodal equations. The next step is really to arrange them and solve them. And so it's a matter of organization. Simplify and organize. And we'll talk about that. But before that, I want to point out something. You see the way I have, when writing these equations, I had all these little currents that I defined. And it looks like, I guess my inclination is to draw them from left to right. So you might be wondering why I chose the currents in these directions. And the answer is it doesn't matter. Let's take a look, for instance, at what we wrote for node V5. Okay? So I had V1 minus V5 divided by 4 plus 0 minus V2 divided by 5 minus the current going through the 3 ohm resistor minus V5 minus V5 minus V4. It's this term here divided by 3. Okay? Now, if I had chosen this direction instead, here I would have a plus sign. Instead of this minus sign, I would have a plus sign. But then instead of V5 minus V4 divided by 3, I'd have V4 minus V5 divided by 3. Because this current is the other voltage, the reverse of the original voltage divided by 3. So this would become a plus sign, but then here, instead of V5 minus V4, I would have V4 minus V5. So the end result would be the same. Okay? So this is something that, and you can do this for any of these currents that I have drawn here. So this is something that you can practice writing in a few different cases differently, and then seeing that it all leads to the same equations ultimately. Okay. So to first order, it doesn't matter. Okay. Or basically, it doesn't matter. It doesn't change anything to the physics of the circuit. As long as you do things in a way that you can simplify, you're comfortable with simplifying and organizing things later on. So basically, now what you have to do is to go through equations one by one and write them in matrix form. Now, what do I mean by matrix form? This is what I said in yesterday's lecture. Basically, you have 9 unknowns here, and you want to organize them into a vector of unknowns. And your unknowns are V1, V2, V3, V4, V5, V6, V7, and then I0, I think, and I4. Yeah. These are all unknowns. What you want to do is to write all your equations in the form of this matrix. Now, the size of this matrix has to be what? Someone said 9 by 9? That's correct. I have 9 unknowns, and basically I have 9 equations, and I'm just putting all these equations into this matrix. Okay? Now, fortunately, each equation only has a few of the variables in it. You don't see an equation here that has all the node voltages, right? What does that mean? For each equation, you can say, so look at the first equation. For instance, the coefficient of V1, there's something there, and there's V2 and V5 and I4. So only 4 of the variables have coefficients there. It means the coefficient of all the other variables in this equation is 0. And similarly for the rest. So you end up with a relatively sparse matrix, which is good for computation. There was a question? So the question is, do I need a 10th column here? And the answer is no. I have 9 equations, right? And each row of the matrix now will multiply the full vector here, right? So that will give me the left-hand side of each equation. So if you're referring to what now I have on the other side, yes, that would be. But it's not part of this matrix. That's what makes things actually happen in the circuit. That comes from the stimulation, the excitation, the sources. OK? So now I basically have to go through these. And you can see, now the first equation will have something times V1, something times V2, something times V5, something times I4. So it will be something like, well, let's write it actually. For V1, is minus 1 over 4 minus 1 over 2, right? So that's minus 3/4. For V2 is 1 over 2. For V3 is 0. For V4 is 0. For V5 is 1 over 4. For V6 and V7 is 0. And for I4 is minus 1. And for I0 is 0. So, okay? If you multiply that row by that vector, you will get the first equation as long as you have 0 on the other side, right? This is just a multiplication of a matrix by a vector. So that's your first equation represented in this matrix form. Now let's look at the second equation. There you have V1, V2, V5, V3, V4 also. So you will have, V1, V2, V3, V4, V5, right? And for everything else, you will have 0. So you will have something for V1, something for V2, V3, V4, V5, and then 0, 0, 0, 0. And on the right-hand side, you have 0. And then you can continue this. You will see that in some of the equations, there are also constants, right? You see that the first one in equation 4, that 8. And if I'm writing things in this matrix form, it means I'm bringing the constant to the right-hand side. I'll have a minus 8 on the 4th line. And then it goes on. And on the 7th line, I have an 8 going to the right-hand side. And then 0. So this has to be completed. But it's purely algebra, just to simplify, so that you can write all these things in this form. Each row multiplying the column will be equal to what the constant you have on the same row on the right-hand side. And so if you call this, let's call this matrix A, and this is, let's say, your unknown vector. And this is basically your source vector. Then, so let's call this maybe source. Oh. So you're saying you're dealing with this matrix equation, A times V equals S. And so you can find V as simply, A inverse times S. And so this is something that you can program easily into a programmable calculator or a computer. And I would really recommend that, especially given that most of you guys are interested in software, that you go write a small Python script or MATLAB script to solve. And basically, you've built your first circuit solver on the computer. And there are libraries that take matrix inverses and such. So you don't need to do the whole thing, right? But just the approach. OK, so this is it. Now, there's one thing I want to point out, and that's about the sign, the signs of these elements. It's more common to write this such that the diagonal elements are positive. OK? It doesn't have to be that way. But so here's a question for you guys. can I just flip the sign on all the elements on one row? Am I allowed to do that? Yes, I am, because what that means is I have taken my equation. So let's take equation number 1. I can multiply both sides of that equation by -1. The equation will not change, right? And in that case, I'll end up with all positive elements. Sorry, for V1, it will be positive. So I'll have positive 3 over 4, negative 1 over 2, negative 1 over 4, positive 1. And on the other side, I have 0, so it won't change anything, right? So if I do that, it will just look like this. Same thing. OK? The equation hasn't changed. And I'm doing that for the whole row, right? Each row is an independent equation. You don't need to do it. The answer is it's more conventional to do it like that. You will see, or at least the conventions that I've seen, when people talk about giving you a recipe, and you might remember from the last week's lecture, where these coefficients that you see here, for V1, we ended up with 1 over 4 and 1 over 2, right? If you look at that. That's not a coincidence. That's because you had a 4 ohm and a 2 ohm resistor attached to node 1. And so in recipes that people will give you, they will say, on diagonal elements, put the sum of the inverses of the resistances that are connected to that node. And on off-diagonal elements, put the negative of the resistances that connect those nodes. So for instance, on the off-diagonal element 1, 2, so row 1, column 2, put the inverse of the resistance that connects node 1 and 2 with a negative sign. So that's kind of a recipe. And you want to be consistent. Again, the equation doesn't change if you add a negative or not, right? So you might as well say, well, no, I choose to have my diagonal elements negative, the other ones positive. Doesn't matter. But so the reason I mentioned this is, again, there's nothing really conceptual there. But if you guys see recipes that say that, all of a sudden I don't want you to be shocked to say, oh, how come I ended up with a negative on the diagonal? Just so that you've seen it, right? So this is an example of nodal analysis for a pretty big problem that has all these things. Okay. Voltage sources and current sources, dependent and independent. Now, of course, once I have solved this, so let's say I have V1 and V2. From that, I can calculate the current I3. I have V1 and V5. From that, I can calculate the current I1. And then right here, I can say that, yeah, I have I3 going in, 5 I1 leaving. And so from that, I can calculate the short circuit current. OK? The rest is really just practicing more examples. And you have some examples in your assignments. And of course, again, remember, if you choose to multiply any given equation by a minus sign, then pay attention to the right-hand side too, right? So instead of -8, then you would have a +8 there, right? So for each equation, you have to pay attention to. All right, so this was the example of nodal analysis. I'd like to do one more problem today, and that's a source transformation problem. So find this equivalent resistance using source transformation. and this is the circuit. So I'm looking here between these 2 points, and I'm interested in the equivalent resistance of this circuit. Using source transformation. So let's have you guys spend a couple of minutes on it on your own. So source transformation means to basically go back and forth between Thevenin and Norton equivalents of chunks of the circuit to be able to simplify in steps. Okay, maybe we should take a look together. So it's really just about going in steps. So we want to identify things that would simplify the solution for us. And so let's see, for instance, if I take the voltage source and the 1 ohm resistor. Well, OK, first of all, before that, I forgot to mention this. If I want to measure the equivalent resistance, and because I have these dependent sources, so it's not a simple matter of just series and parallel resistors or Y delta transform. I actually have to do it on paper the way I would do it in the lab, which is you use instruments where you apply a voltage. So you apply a voltage here. So let's say V0, and measure the current, right? So this ammeter doesn't really do anything in the circuit like that because it doesn't take any voltage. So if you measure this current, the equivalent resistance will be V0 by I0. And the value of V0 doesn't matter because this is a linear circuit. Things will scale. If V0 is 5 times bigger, I0 will come out as 5 times bigger. The ratio will stay the same. Okay? So we talked about this in class. So this is basically what I'm doing. And I want to simplify this. Okay? Now, if I look at what I have up here, between the 2 points, between the 2 terminals of that box, I basically have a Norton circuit, right? If I convert that to sorry, I have a Thevenin circuit. Okay, I have a Thevenin circuit. And if I convert that to a Norton circuit, I'll end up with a resistor in parallel with that, the horizontal resistor there, right? For which I forgot to put the value. So this is, say, 6 ohm. Okay. So now if I want to replace this with a Thevenin equivalent, the resistor stays the same, but now I have a current source in parallel with a resistor. It's the same resistor, 1 ohm. And the value of the current source, remember the relationship between Thevenin and Norton. The value of the current source is what? The value of the current source, so in the Norton representation, recall that the open circuit voltage was just Rn times In, like the example we saw earlier, right? The open circuit in the Thevenin representation was what? Was just V Thevenin. If it's open, there's no drop across the resistor, it's just V Thevenin. So V Thevenin is simply Rn In, or In is Vth by Rn. So this current is simply the voltage 2Vx divided by the 1 ohm resistor. Maybe 1 is a bad number here because we want to see something more concrete. So let's say 3 ohm. So this would be 2Vx divided by 3. And notice the direction. Okay, again, go back to your source transformation. Recall the discussion we had about the direction. That this is not arbitrary. It has to be such that the open circuit voltage that you get from both circuits has the same direction. And that's why this is how I've represented it. Now, the next step is the rest of the circuit it's just as it is. But there is also something here that's a Norton circuit, the 3 ohm resistor in parallel with a current source with the 3 Vx. That's a Norton circuit. This one I'll replace with its, well, maybe I'll do this in the next step. Okay, so let's write this down as it is. Okay. Now, hopefully you see the merit of my having done that conversion from Thevenin to Norton at the top, because now I have the 3 ohm and 6 ohm resistors in parallel that I can just combine. The combination of those is just 2 ohms. Now I have that I can combine. And then I have a Norton equivalent at the top that I can change to a Thevenin. And I have another Norton down here that I can change to a Thevenin. And then I'll end up with one big loop, which is a lot easier to deal with, right? One big loop at the top, plus this little loop that includes the voltage source. So my goal is basically now to convert this to a Norton, sorry, to a Thevenin. So how do I deal with Vx now? If I start converting things, all of a sudden, so let's try that, okay? So let's convert that. So 3 and 6 in parallel are 2 ohms, right? So I have 2 ohms with that current source. So the open circuit voltage will be the current times 2, so that's 4/3 of Vx. And pay attention to the direction. So let's say that this is just 2 ohms. Okay. But and then this other one, this is another Norton that can be turned into a Thevenin. So that's 3 times 3, so that's 9 Vx in this direction. And it's 3 ohm resistance. And that's that, right? And then I have my 5 ohm and 8 ohm. Okay? So I have done this, and arguably this is a simpler circuit maybe to solve because I have just 2 loops. It's easy to write KVL, KCLs, or mesh analysis. And I can maybe combine the 2 ohm and 3 ohm, yeah? Yeah? Okay, so let's say I combine them. I say this is 5 ohm. Okay, great. I have 4/3 of Vx at the top, 9 Vx here. Where is Vx? So Vx was the voltage across that 6 ohm resistor, or you might say between those 2 nodes. It's gone. So I have to be careful.
You need to stretch those nodes
Yeah. So this is the nodes that we are talking about, right? These are the nodes. So Vx is the voltage difference between those in this circuit, right? So I should be very careful as I'm doing my conversions not to disturb those nodes too much, right? Because up to this point, you see, if I had, you see, here I have still kept this node. That left node is still there. And here, that node is still there. And I had my two ohm and 3 ohm like this. You see, that node is still not disturbed. These nodes are still there. That Vx is still there. You guys see that? I converted this box, but I didn't disturb that node. And the box on top, but I didn't, or the circle on top, but I didn't disturb those nodes. So I haven't lost that Vx. Vx is still where it was. I have just represented chunks that are connected to Vx in ways that would allow me to simplify things. Okay, so this is what I wanted to emphasize. Sometimes you might have a current that's controlling something else. You have to be careful not to lose it during your transform. Okay. So the message is, don't lose the variables on which the dependent sources depend. Because otherwise, then what are you going to do? Okay, so if you have it like this is basically as simple as it gets. Now, the next step is just to solve this using, if you want, KVL, KCL directly or mesh analysis. Okay, so this is where we have to stop today. See you guys tomorrow. Thank you.